Hello, hello, hello. Welcome back for lecture 11. In case you're wondering, I am wearing the exact same shirt that I was wearing for lecture 10. That's because I'm recording both these lectures on the same day, so don't think that's weird that I'm wearing the same shirt 2 days in a row, because I'm not wearing the same shirt 2 days in a row. Um, yes, yes, just yeah. Anyway, so today's lecture 11. It's the continuation and the conclusion of excuse me, alkyl halides and SN1, SN2, SNE2, SN1, S and E1 reactions. And I just wanted to say that um, this is the lecture. This right here is a lecture that really bridges the point where you just kind of know chemistry and and you really know chemistry. What I mean by that is, beginning in this lecture, you'll be able to look at a product, right? Like something you want to build, a molecule, any molecule that you want to build, right? And you'll be able to start putting together pieces of smaller molecules, you know, and using your tools and what you learned in organic chemistry thus far to build that molecule out of scratch, which is incredibly valuable, right? I mean, the key to all of drug discovery and things like that is, and discovering all kinds of new products is having a molecule that's novel, right? But the problem is that novel molecule is super, difficult to either make, or it's very scarce in natural resources. And so, if you're able to make this very special molecule, this drug, right, or this plastic, or whatever, right, using really cheap products, really cheap starting materials, right, then that's enormous. That is a huge accomplishment, and that's a set of tools that will suit you well in life, right? That will suit you well in life, because really this class is all about problem solving, and the problem in this class is, I have a molecule. How do I build it out of scratch? Right? How do I build it with just small, tiny little molecules? Make this one huge molecule that actually does something for some people, right? That helps people. So, thus far, I hope you've been enjoying the lectures and learning a lot. And I really hope that you take away from the class, even though this class has been very fast, and we've been covering so much information. Uh, the thing I really want you to take away from this class is problem solving skills. Okay, so let's go ahead and get started. Excuse me, and finish up lecture 11. Right, we're in the last circuit. No, is that right? Circuit of a race? Last lane of a race? No, last circuit, last round, whatever of this particular chapter. All right, so sorry about that. I need to switch views. I changed the slides without even switching the views to presentation. I could just talk to you like this the entire time. You don't even have to see the PowerPoint, and I'll just be a talking head, for the next hour or so. And you just don't see anything. You just listen to what I say and write it all down. Do you guys want to do that? I mean, that's fine with me, because I have really bad handwriting. So no, I'm just kidding. All right, let's get started. So lecture 11, alkyl halides and nucleophilic substitutions and eliminations reactions continued. Okay. So we already talked about in the last lecture SN2 reactions, right? Substitution nucleophilic 2, right? Bimolecular two molecules. We also talked about E2, which is elimination reactions, 2 molecules, right? Now we're going to jump into the unimolecular reactions. That's SN1 and that's SNE1, okay? Excuse me. So consider the following reaction, where a substitution and elimination products are formed when dissolving, right? And so what that means is that ETOH here is not actually acting like a nucleophile. It's just a solvent, okay? A nucleophile or a base. It's just a solvent, right? And in a unimolecular reaction, right, the leaving group is such a good leaving group that in the solvent that it's in, it just leaves, right? Leaving you with a carbocation. Okay? And then after you get the carbocation, one of two things can happen. You can either have the substitution product, right? The substitution product, where this ETOH goes over as ETOH, not as the ethoxide, and attacks that does a nucleophilic attack on the carbocation, right? And thus what you've done here is that you've substituted the bromine with the ETO, right? Okay. Or the other thing that can happen is you can do the use the ETOH as a base, and it can pull off a proton, right? Pull off a proton, and then that bond comes down. It makes a double bond, right? Filling in the carbocation, and that's how you get the elimination product, right? So we'll go through that in much more detail in just a second, but let's just keep on track here, right? The substrate is a tertiary alkyl halide, right? So an SN2 reaction is not possible. The reagent is ETOH, which is not a strong base, and so the E2 elimination is unlikely. So what that means then is that since we have a weak base, right? It's not a strong base, right? Then it can't do the E2. You have to have a strong base to do the E2 reaction, right? And then since it's a tertiary alkyl halide, it's got all this steric hindrance over here, right? So it can't do a backside attack to do the SN2 reaction. Since those two things are in play, right? They still see experimentally that these things are being made, right? These things are being made. Well, how is that possible? It's possible because the bromine can just leave as a leaving group, because it's a wonderful leaving group in the ETOH solvent, and then the reactions occur, right, in SN2 style or in E2 style, right? But this is just a single molecule here, just breaking apart, right? And that's why we call it a unimolecular or single molecule reaction, right? So it turns out that the formation of substitution and elimination products follow first order kinetics, right? Which means that it confirms that neither the SN2 or the E2 is occurring, right? Because remember, when we had E2 or SN2, it was actually second order kinetics, right? Where the rate depended on both the concentration and the rate depended on both the concentration of the substrate and the nucleophile, right? Yes, the nucleophile. Or the base, that's what I was thinking of, or the base, right? But here, the rate K is only reflective of the substrate. So, same first step, right? The mechanism of a substitution and elimination reaction, in this case, both start with the same step, right? Which is ionization of the substrate, which is what I showed you in the previous slide. Here, the bromine, the bromine leaves as a bromide leaving group, just on its own, right? And that leaves you with the tertiary carbocation, right? This tertiary carbocation intermediate. And then this can proceed either with a substitution reaction, which is SN1, or proceed with an elimination reaction, which is E1, right? Excuse me, man, my throat is really itchy today. So after the carbocation is formed, right, it will either undergo substitution or elimination depending on how it reacts with the solvent ETOH, right, which you saw in the previous slide I drew already, which it will show you again here officially. The substitution reaction of the tertiary substrate in an alcohol solvent like E2H proceeds through a stepwise mechanism, right? So here we have the carbocation, and like I was saying before, the ETOH attacks as is, not like ethoxide, but as is, and nucleophilic attacks the carbocation, right? This leaves you with I was about to say transition state, an intermediate, where you have the oxygen attached to the tertiary carbocation, or the carbon, right? That alpha carbon right there. And you still have a proton attached to it. So, excuse me, at this point, At this point, another ETOH can come over, right, with its lone pairs, pull off that proton, and then the bond from that proton to that oxygen goes into the oxygen, giving you a neutral charge, and now you have the substitution product, right? You have the substitution product. The entire mechanism actually is 3 steps, but the last step is just a proton transfer. So this is actually called a solvolysis, right? Because the nucleophile is also the solvent, right? And we call it solvolysis because literally solvo is solvent and lysis means to break a bond. So the solvent is assisting in breaking a bond, right? The highest energy transition state in the SN1 is for the formation of the carbocation intermediate, which makes sense, right? Here's the bromine breaking off. You lose the bromine as a leaving group, right? And that EA right there, the energy of activation right there, is at its highest when we're trying to reach the carbocation intermediate, right? Excuse me. So know then that the loss of the leaving group here, right, is the rate determining step, right? The loss of the leaving group and the formation of the carbocation is the rate determining step. It determines what our rate K is, right? Afterwards, we have the nucleophilic attack by the ethanol, and we get a brief transition state here, and then down to the intermediate state with another intermediate structure there, right? Intermediate structure there. And then another brief transition state here where we do the proton transfer, right? And we get our product, which is this substituted tertiary alkyl halide, which is now an alkyl ethoxide, right? Good stuff. Since the formation of the carbocation requires only ionization of the substrate, the rate of its formation depends only on the substrate, which makes sense, right? And so the reaction follows first order kinetics, where the rate K equals the rate K. The rate equals K, the concentration of the substrate. I'm trying to talk too fast. The rate of the SN1 reaction, the rate of the SN1 substitution depends only on the substrate, right? And that's why we call this the SN1, the substitution, right? Nucleophilic, unimolecular, right? Unimolecular. Good stuff. Good stuff. First order kinetics too, right? Because there's just the one there as the exponent, so it's first order. Remember that. Oh, it says it right there. My bad. So some more details about this mechanism, right? A substitution reaction that occurs stepwise, where the leaving group first leaves to form the carbocation intermediate, is followed by the nucleophilic attack called an SN1 substitution, right? We just did this. It's reviewing it again for us, right? Our leaving group leaves. Here's the X, the alkyl halide, with the leaving group, the halide, leaving. And here's your leaving alkyl halide, your leaving halide. And so you're left with the tertiary carbocation here, right? The nucleophile comes over, does its nucleophilic attack on the carbocation, and then now you have the nucleophile attached to the carbon now, right? So quite simply, right, you ended up with still a substitution reaction because the nucleophile took the place of the halide, right? But the difference between this and the SN2 reaction is that number one, there was no need for a backside attack, right? But then also, number two, the reaction started with just the substrate ionizing, such that the leaving group left on its own. Okay. So remember that when a nucleophile is a neutral species, such as an alcohol, there will always be a protein transfer after the nucleophilic attack. Okay. So the elimination of the elimination reaction, though. Sorry. So that takes us to the elimination reaction. The elimination reaction of a tertiary substrate is in an alcohol-like solvent, ETOH, proceeds through its two-step stepwise mechanism. Again, we begin with the bromine leaving group leaving on its own, okay? And then the ETOH acts as a base. And so it comes over here and pulls off a beta hydrogen, a beta carbon hydrogen. That bond comes down, makes a double bond to fill in this carbocation here, and we get our elimination product, which is the alkene, right? Almost exactly the same thing as the E2, right? Except the leaving group lost its leaving group. Wait, the substrate, alkyl halide, lost its leaving group on its own, right? We didn't have to have the base come over and deprotonate the beta carbon to form the bond to knock off the leaving group. Okay. Here, E2H is serving as a base, not a nucleophile, to deprotonate the carbocation and form the alkene. So, like SN1, the E1 mechanism is unimolecular and follows the same kind of kinetics. The rate of E1 is the same as S1. In both cases, the rate determining step of this formation of the carbocation intermediate. Excuse me. So, I don't know why I read that sentence. Both E1 and S1 and SN1 share the same rate determining step, which is the step of forming the carbocation right here, right? Because that step is all dependent on this transition state up here, where we lose the leaving group. Okay, loss of the leaving group up here. Okay, so again, rate K is just the substrate concentration, right? Just substrate concentration. So we can get the E1 product, which is the alkene, or the SN1 product, which is the nucleophile substituted alkene. Alkyl? Carbon. Yeah. And you can also see too the potential energy of the SN1 is lower than the E1, right? Product. So they're common. So in E1, SN1 and E1 rearrangements, right? They're pretty common because SN1 and E1 reactions proceed through a carbocation. Recall from a previous lecture, maybe the one not yesterday or the one before. I think it was the one before that, where a carbocation will rearrange itself through hydride or methide shift to form a more stable carbon. Excuse me, and that was the one where I was talking about. A tertiary carbon is more stable than a secondary carbon. A secondary carbon is more stable than the primary carbon, right? Carbocation. And then the thing that's more stable than even a tertiary carbocation is a resonance stabilized carbocation, right? And so here, in this case, we have another alkyl halide with some heat and some water, right? We get both the SN1 product that we would expect, right? Where the nucleophile here is the substituted, right? The nucleophile here, the water or hydroxide, is substituted in for the bromine, right? Or we can get the SN1 product after the hydride shift, right? After the hydride shift. So imagine this. We have the bromine leaving, right? The bromine leaves, and it leaves behind a carbocation on that carbon. But that's a secondary carbocation, right? I mean, would it want to do that? Would it want to stay that way? No, not really, right? And so it will move so that it will move or shift so that the carbocation is now at that position, right? The carbocation is now at that position, making a tertiary carbocation, and that's why the hydroxide ends up down here instead of up here. Okay? The same thing is true of the elimination products too, right? The same thing is true of the elimination products too, right? So here, I'm sorry, we have elimination products here. I got confused. This is just another one, right? Where This is again another hydride shift, right? Or a methide shift this time. Sorry, a methide shift this time, where the bromine leaves again, okay, and you'll be left with a carbocation there, right? But to make it a more stabilized carbocation, this methide will shift over here, right? so that the carbocation ends up over here, and now it's a tertiary carbocation again, right, on this carbon right here, okay? And that's how we end up with this shift there, right, where the hydroxyl, or the alcohol, right, or the water, right, goes and does a nucleophilic attack on this carbocation instead of this carbocation, because it can happen right after the methide shift, right? The nucleophile can attack right after the methide shift. When a primary substrate is reacted under solvolysis conditions, or solvolysis, oh, that's how you say that. Under solvolysis conditions, only the product resulting from the rearrangement is observed, which makes sense, right? Because the product, so again, we're going to do another rearrangement here, right, where the bromine leaves on its own as a leaving group, and then we'll have right now, like there, a positive carbocation on that one little carbon right there as a primary. Oof, that's not very stable. So we can do a shift here, right? So that, sorry, my arrow went the wrong direction there. Oops. What happened here? Draw. There we go. My arrow went the wrong direction. Let me draw that again. We have the bromine leave, right? And that leaves us with a carbocation right there on that carbon, which makes it a primary carbocation. And that's not very stable, right? So we can have a methide shift where this methide comes over here, right? And then you're left with the tertiary carbocation now, which is far more stable, okay? There we go. Forget that line. Forget that line down there. All right. And so the reason why you only get the SN1 product, right? This product only, and not this one right here, is because it went through and did that methide shift first, and so the nucleophile went and did its attack, right, on that carbon instead of the carbon where the bromine came from. All right. So just remember that that if you have a carbocation and it can move somewhere, so that that carbocation can move somewhere through methide or hydride shift to be more stable, most commonly to become either a tertiary carbocation or a resonance stabilized carbocation, right? Then it will do that first, and then you'll have your products. And so you know then that the product that will show is the rearranged product and not the one that's not rearranged. So also remember that primary carbocations are too unstable to form. So in this case, the rearrangement occurs as the leaving group leaves, right? So here, you can see the bromine is leaving, right, as bromide leaving group, and the methide shift occurs at the same time, because the primary carbocation is just so unstable. And then what I just showed you before, where the nucleophile comes over, does the attack on the carbocation, and now you have the water attached to the alkane, and then another water comes over, pulls off a proton, right, and then it refills that empty gap, that empty hole of electron orbital for oxygen, filling it back up again. So now it's neutral again, and now you get the alcohol product, right? You get the alcohol product right there. Okay. And again, just to remind you, right, at the end of all these, there's always a proton transfer. Protein. A protein transfer, no, proton. So, just as a general rule, the better the leaving group, the faster the SN1 or E1 reaction, right? Fluoride here is not a very good leaving group, right? So it's least reactive, but then you get to chlorine, bromine, and iodine, or their iod versions, right? They're ion versions, and they're quite reactive, right? So remember that the rate determining step of the S1 and SN1 and E1 of the alkyl halides is the ionization step and the formation of the carbocation in the halide ion, right? So the more stable the halide ion, the faster the ionization occurs, which means the faster the rate limiting step, right? Intermediate stability of the substrate now, right? So the more stable the carbocation intermediate is, the faster the SN1 or E1 reaction will be too. So in sovolysis, reactions of a primary and a secondary alkyl halide are often formed too slow to observe the formation of the SN1 or E1 products. However, if it's a tertiary alkyl halide, as well as a benzylic or allylic allylic halide, they will undergo sovolysis at a practical rate thanks to the stability of the carbocation intermediates, right? And so we already knew that this carbocation right here is tertiary and it's quite stable, okay? But remember also that even though this is a essentially a primary carbocation right there, right? It still is resonance stabilized, right? This bond can come down here, right, and do resonance. Same with this, right? So both benzylic and allylic carbocations, right, are capable of doing resonance. Remember, that was one of the REO things, right, that I was very sad about when REO died in Twilight, but he didn't die. It was just, you know, I don't know, what was it, a prediction of the future or something that never actually happened. And then someone told me, and I think I've told you this already, but I'll tell you this again. His name's not Ario. His name is Aro, which, wait a second. I'm totally wrong. I'm completely confused. He didn't die. I'm talking, no. My girlfriend would be so upset with me right now. He's supposed to die. He's the bad guy. Aro is the bad guy. It's the doctor father figure in him. That when he died, that's when I was upset. What was his name? Dang, what was his name? Oh God, I can't remember what his name is. Somebody in the comments below, please, if you're watching this on YouTube, tell me who was Edward's, you know, father, the one that saved his life, the doctor. God dang it. What is his name? I could look it up, but I like having the feeling of the aha moment when I figure it out. So sometime on later in this lecture, it'll just come to my head and I'll remember it. But at this point, I don't. So no, I don't know what it is. So if you want to, and you're watching this on YouTube, please remind me who that is. Sorry, I'm still thinking about who that person is. Anyway, next, let's keep going. SN1 and E1, the substrates examples. Okay, so be able to judge whether or not a given alkyl halide will undergo sovolysis, right? E1 or SN1 reaction. In general, a primary and a secondary alkyl halide will only undergo sovolysis if a rearrangement occurs to a more stable carbocation, right? A primary one or secondary one will rearrange to become a tertiary one, right? Or it's resonance stabilized. So tertiary allylic and benzylic alkyl halides will undergo sovolysis to give a mixture of both the SN1 and the E1 products. So here we have a benzylic substrate, okay? And the leaving group is the bromine, and it leaves. Okay, leaving behind our guy that looks like this. All right, and right now, that is actually resonance stabilized. That carbocation is resonance stabilized because of the benzene ring right there, right? And so, quite easily, then, water can come over as a nucleophile and do the attacking there, right? Giving you the S1 substitution product, or the water can come over and pull off the proton from over here. That bond comes down there, giving you the E1 product. Right? The E1 product. Both are observed. So conceptual checkpoints 7.26, 7.27, and 7.32 on Y plus just for you, and all the answers are there. No, I don't know if their answers are there, but it's Y plus is very helpful. Carlisle, that's his name. Dang, Carlisle's the doctor. He's the one that I was very upset about when he died, supposedly, but he didn't die because it was just one of that girl vampire ones that can see the future's visions or something. Anyway, see, I knew it'd come to me. I just knew it. So like we saw with E2 eliminations, is it possible for an E1 elimination to yield more than just one regional isomer, as in the following example? Right? So here, again, we have the chlorine leaving as a leaving group, and we'll end up with a tertiary carbocation, right? Our elimination products, right, are these two here, because we have protons that we can pull from here, or protons we can pull from here, right? And that depended on whether or not you had a bulky base, remember that? Or a streamlined base. But then we also have the substitution product, right? Substitution product. If we had the water just come over here and just, do a substitution reaction, right? Nucleophilic attack substitution reaction. So E1 reactions will always give the most stable alkene as the major product, which is the most substituted alkene. This one right here is only substituted on two sides, right? But this one here is substituted on three sides. Okay? So this one is the major. This one is the major product, the major elimination product. Okay. So E1 reactions are regioselective, but we cannot control the regioselectivity like we can with E2 reactions. Oops, I just said. Well, what I said was it's kind of like this is kind of like when we were doing the thing with the bulky bases and the streamlined bases, and we could pick which one we wanted to do. So on an E2 reaction, you can actually pick, right, which one, depending on the either the base was bulky or if the base was streamlined, right? It would choose. If it was streamlined, it would choose the CH2s, the H's from the CH2, and then if it was bulky, then it would choose the proton from the methyl group, right? Well, that may be true of an E2 reaction, right? But as this last line just stated, right, that's not true of an E1 reaction. Okay, it doesn't matter with an E1 reaction which one you use. It is further possible to obtain several alkene stereoisomers with an E1 reaction, as in with the following example, right? Again, we have the bromine leaving as a leaving group, okay? Leaves us with this carbocation here. And we can get this double bond from removing one of these protons over here. We can also get the other double bond. Well, it's the same double bond, but this time it's pointed down this way, right? Instead of pointing up that way, and we can get that by pulling off the other proton, right? Because there are two protons sitting there, and then we can do lost my train of thought again. You can also pull off the proton from up here, right? And then that would give you this one. Okay, and then again we have our substitution product. Okay, there are also protons over here that you can pull off that will yield you those and that. Okay, so it still holds true that an E1 reaction will still give the most will give the most stable alkene, right, as a major product. The two stereoisomers, when two stereoisomers obtained, the least sterically hindered isomer is the more stable one, right? So which one is the least sterically hindered one here, I would say probably this one, right? Because it's all open. Yeah, this one's open too, but it's got its double bond there, right? So yeah, this is the least sterically hindered one. Which I didn't even notice that it already says up there that that's the one. So I keep telling you guys to be careful what you're reading, but I always forget to read it myself. So E1 reactions are stereoselective, but realize that a mixture of all the possible products can still be obtained. Okay, so SN1 stereoselectivity in two products, right? When an alpha carbon in an SN1 reaction is chiral, right, we obtain two substitution products that have opposite configurations at the reactive carbon. Okay, so this is very, very similar, right, to doing like the backside attack reaction, right, of the SN2 reaction, but not exactly, right? The nucleophile does not do a backside attack, and so this is why you get two products, the inversion product and the retention product, right? Whereas on the SN2 reaction, you only get the inversion product, okay? Because on the SN2, that's the only one you get the backside attack. But here, right, since the bromine is leaving on its own, the nucleophile can attack on either side, okay? That way or that way, right? And so if it does it from the backside only, if it doesn't from the backside, you get the inversion, right? Where all the substituents are inverted, right? And you get a different chirality, different configuration, right? But you also get the retention of the configuration too, where all these are still in the same positions as they were with the substrate. Okay. So that's the big difference there between the SN2 reaction and SN1 reaction, right? In the SN2 reaction, it did a backside attack because the bromine or whatever the leaving group was sterically hindering the places where the nucleophile could attack. So the nucleophile had no choice but to attack from the backside where the bromine wasn't, right? But in an SN1 reaction, the bromines are already left, right? That's the first step of every unimolecular reaction. The bromine, the leaving group, has already left, so it actually leaves both exposed, and then now they can attack from either side, right? So you get a mixture of both of those. So interestingly enough, and let me actually move my head out the way here for this part. There we go. Interestingly enough, though, even though the bromine has left already, right, the nucleophilic attack is still hindered a little bit because the ions still kind of the ions still form a pair with each other, right? And so while the bromine is not like covalently attached to that carbon anymore, it's still hanging around because the ions are attracted to each other, which does hinder the nucleophilic attack a little bit, right? So what happens then is you still get mostly inversion product because it's unhindered, but you also get the retention product too, right? But mostly it's inversion product, right? More than 50% of it will be the inversion product, which is like a nucleophilic SN2 reaction, right, from the backside. But you also get some retention of the retention product too, where the substituents all stay the same as in the same positions as the substrate. Okay, again, that's the big difference between the SN2 and the SN1 reaction. In the SN2, you will only get inversion product, right? Whereas in the SN1, you will get both inversion product and retention product, albeit more inversion product than retention, but still retention product is still there. So, predicting products, mixtures. By now, it should be clear that a number of factors affect the products formed when reacting with an alkyl halide with the nucleophile or base, right? And the substrate reagent and the solvent, right? So it should be clear that in many cases, a mixture of the substitution or elimination products will be obtained, okay? And I forgot to bring myself back, but that's okay because you need to see this part anyway. Again, we get another leaving group going on there. We have hydroxide as the nucleophile here, or the base here. So we get a mixture of both E2 major and minor products, and we get the substitution product as well, right? So the point of this slide is just to remember that quite often, more often than not, it's always going to be a mixture, right? Because the nucleophile or the base can act as both, either nucleophile or base, and it will give you the elimination products, major and minor, based on which proton it deprotonates, or yeah, based on which beta carbon it deprotonates to get its proton, right? And then the substitution product, because the nucleophile will take the place of the halide, right? And let me bring myself back now. There I am. So, single products, predicting products. It is possible for a given substrate that only one mechanism will occur, right? So here we have iodine, tert butyl iodine, I guess it would be called, right? And it's interacting with sodium methoxide here, and the only product that you get here is the elimination product, right? So in order to understand how to use these reactions to transform alkylides into a desired compound, one must be able to predict all the products that will form in a given reaction, as well as the major and minor products. So here's some steps to figuring out what the products are going to be. And don't worry, we'll go through each one very detailed-wise, very laboriously. To successfully predict the product or products formed in a given reaction, we can follow this three-step analysis. The first step is to determine the function of the reagent, right? Will it be a nucleophile or will it be a base? Okay. Then analyze the substrate and determine what the expected mechanism will be. Will it be SN2, E2, SN1, or E1? And then consider any relevant regiochemical and stereochemical requirements, right? Will it be cis or trans? Will it be RS? That kind of thing. Is it going to be inversion or, or retention? That kind of thing. Okay? So, let's go through these one by one. Step 1. Remember what kind of reagents promote SN1, SN2, E1, and E2 reactions, right? So in SN2, right, usually a strong nucleophile is required to do an SN2 reaction. An E2 reaction requires a strong base, right? And SN1 requires a weak nucleophile, and E1 requires a weak base, which makes sense, right? Because in both of these down here, the ionization occurs before there's an attack, right? And so it doesn't need to be a strong nucleophile because the leaving group already left. Whereas up here for the twos, right, the SN2 and E2s, right, they've got to be strong in whatever they're doing here, right? Because the leaving group is still there. You got to kick the leaving group off. Okay? So the following table is a good resource for categorizing reagents and mechanisms that they will promote. So we have sodium hydride here, and DBN and DBU, which I have no idea what those are, right? But those are strong bases but weak nucleophiles. Then we have hydroxide, methoxide, and ethoxide, right? Both a strong base and strong nucleophile, right? Those promote the SN2s and the E2s. These promote the E2s, right? Iodine, bromine, iodide, bromide, chloride, lost my train of thought there, sulfide, and then thiol, and thiol again, and then more thiol. Sulfurs, basically, right? Those are all weak base, strong nucleophiles. They promote the SN1, SN2 reaction, right? And then if you have a weak base, weak nucleophile, which is water, methanol, and ethanol, that can promote the unimolecular reactions, right? The unimolecular reactions, SN1 and E1. So step 2, once you've determined what the mechanism is that will be favored by each reagent, right? analyze the substrate. Is it tertiary, primary, or secondary, right? To see what mechanism will dominate. For example, right, say we have a very strong base, okay, like hydroxide, and the substrate is a tertiary substrate. Then the mechanism will be an E2 reaction, right? Will be an E2 reaction. Notice E1 is over here all the way, right? Because the only time you can have an E1 reaction is if you have a weak base, weak nucleophile, with a tertiary, right? Tertiary alkyl halide. So both of these charts right here, right? The chart that I showed you before with the different nucleophiles and bases and their strengths in the previous slide, and then this slide, both of these charts are in your book, so they're very helpful. Step 3: after analyzing the reagent and the substrate, you can say which mechanisms will occur, right? So draw out all the possible regio and stereoisomers, and then choose the major product using the guidelines that you learned in the previous slides, right? So, for example, for SN2, you will observe a single product, right? In which the product is an inversion of the configuration of the alpha carbon from the substrate, right? Because of the backside attack. In an SN2 reaction, nucleophiles attack the alpha carbon, right? Leaving the leaving group connected, where the leaving group is connected, right? And then the nucleophile replaces the leaving group with an inversion of configuration, right? That is, in a nutshell, an SN2 reaction. For an E2, right, you got to draw all the possible alkene isomers. Only alkenes which result from a beta hydrogen that is I had problems saying this last time too, in the last lecture too. Anti-periplanar to the leaving group can form, right? So anti-periplanar means coplanar, right? Like opposite each other. They have to be opposite each other, right? So either they're in line, right, because they're in line with the piece of paper, so that's opposite each other, or one is heading out of the paper and the other one's going into the paper, right? That's anti-periplanar, right? And then if a bulky base is used, the Hoffman product is the major product, right? And then if it's a streamlined non-bulky base, then the most stable alkene is the major product, right? And if you recall, that was the Zetzev product, right? The Zetzev product. And that's E2. For an SN1, though, right, draw the carbocation intermediate and consider if it will rearrange first. Because remember, right, you will always get the product with the rearranged carbocation first that's more stable before you get the other one, right? Sometimes you won't even get the other one if it's like a primary, because those primary carbocations aren't very stable at all, okay? If it rearranges, draw the rearranged result, right, carbocation, and then attach a nucleophile to it. If a chiral carbon is formed by the attack of a nucleophile, then two products are formed, the R and S versions, configurations, so draw them both. And then for E1, right, draw the carbocation formed with the loss of a leaving group and see if it will rearrange again, right? Rearrange into a tertiary carbocation, okay? Or maybe even a resonance stabilized carbocation. Then draw all the possible alkene isomers resulting from the elimination of the beta hydrogen, right? And then all possible alkene stereoisomers will form, right? E1 is not stereospecific, right? Not like E2 is when you have a bulky base or you have a streamlined base, right? The major product will always be the most stable alkene, right? Which is the Zetzev product again. Practice these steps in Skill Builder 7.7 on Wiley Plus, just for you and me and for you too. Good luck. So let's go through this with an example, okay? So predict the product of the following reaction and label the major product. Well, let's go through this stepwise again, okay? Step 1, analyze the reagent, okay? We have sodium hydroxide here, okay? Well, sodium hydroxide is a strong base, and it's a strong nucleophile. So what does that mean? That means it's either going to be an SN2 or an SN1. That's going to be an SN2 or an E2 reaction, right? Okay? And just so that you can see the rest of the step 2, let me move my head. There we go. Step 2, look at the substrate. The substrate here is a 1, 2. So it's a secondary halide, alkyl halide, right? Since it's a secondary alkyl halide, SN2 and E2 will occur, but the E2 will dominate because the secondary substrates are somewhat hindered and the backside attack is more difficult, right? Let's just make sure that's true. We'll go back to the chart here, right? Here we go. Strong base, strong nucleophile, right? Secondary, E2. Okay? Cool. Then step 3, consider the regio and stereochemical requirements. For an SN2 product, backside gives attack of inversion of configuration. We already established that this was going to be, I'm sorry, let me bring myself back. We already established that this was going to be an E2 reaction, right? So you don't even really have to do this part with the substitution, the SN2 reaction, right? But it's good to practice, okay? So just like we saw before, since this is SN2, right, we have hydroxide coming over. Okay, hydroxide coming over. And it does a backside attack, like that. Okay, and the bromine leaves. Okay, and then we get the inverted, right? We get the inverted product, right? This methyl used to be right here coming out at you, but now the methyl is going into the piece of paper, right? So that's your SN2 product. Again, we've established already using that chart that it's only an E2 reaction, right? It favors the E2 reaction, so we really don't have to do this, but it's good to know. Okay, so now let's consider the regio and stereochemical requirements for the E2 product, right? So the first thing we have to do is figure out all the beta hydrogens that can be anti-periplanar to the leaving group. Well, what that means is that we're going to have to be able to rotate this bond, right? So that we can get the, see which protons are available, that bond and this bond too, right here, right? To see which protons that are available on the beta carbons that can be periplanar, anti-periplanar to the leaving group bromine right here, right? The methyl group down here is pretty easy because they're all the same proton, so all of them are susceptible for deprotonation and leaving group, and then the leaving group leaving. But the one up here, though, right? We have an HA here, a proton A here, and a proton B here. Okay, and we rotate that bond so that A is pointed downwards, right? Pointed downwards that way, right? So that it's in the same plane, or also known as anti-periplanar with the bromine, right? And then the base here, which is hydroxide, comes over and pulls out that proton, right? Let me just clear out all these arrows here. It's getting a little confusing. The base comes over. Oops. Not the base, but it is a base. But it's a hydroxide, comes over. Pulls out that proton. That bond comes down here, making the double bond here. And then the leaving group leaves. Bromide leaves. Right? And when we have the proton A rotated such that it's anti-periplanar with the leaving group, it gives us the trans-alkene product. Right? It gives us a trans-alkene product. We do that again where we rotate it so that the proton B here, right? The proton B here is the one that's getting deprotonated. Same thing happens again. Base comes over, pulls the proton off. Oops. I overshot that proton there, that arrow there, right? The arrow is not supposed to go to the bond. It's supposed to go to the proton, right? So I'm going to have to do that again. It goes to the proton. That comes down here. And since we rotated that one more step over, right, to get it to be anti-periplanar to the leaving group, we do form the double bond, leaving group leaves, and this time we make the cis product, right? The trans and the cis product. And then we can do the elimination product for C, proton C, which is pretty easy because it's always going to be this. They're all the same proton, right? And it's rotating about that single bond there on the methyl, all right? Pull off that proton there, that comes down there. We get a double bond there, and then the group, and then the leaving group leaves, right? Bromine leaves, and then that leaves us with the terminal alkene there for the elimination of HC. Okay, so those are all the regio and stereochemical possibilities for the E2 product. Okay. Now that we have all of the resulting SN2 and E2 products, now we need to label what the major product is, right? So E2 was the major pathway, right? And the base is not hindered, so we know that the ZZ product, or the most stable alkene, is the major product, right? And and that would be the transalkene. That would be the transalkene, right? That's the major product. Okay. Of course, we have some starting material left over here. We don't even have the SN2 product listed there because really we've already decided that the major pathway is the E2 pathway, right? So do some more practice with skill builder. Did they forget the word skill builder in 7.28? Okay. Oh, I forgot to bring myself back. There I am. Okay. Practice skill builder 7.28 in Wiley Plus. Okay. Okay. So there are a variety of alternative alkyl halides for substitution and elimination reactions, and these are also known as the alkyl sulfonates. Oh, remember last lecture, and I was like, that leaving group, I have no idea what that thing is called. That's what this is called. It's called a sulfonate, right? We have 3 sulfonates here. We have mesylate group, or alkyl mesylate. We also have alkyl tosylate, and we have alkyl triflate, right? And all these sulfonates, these alkyl sulfonates, they're called sulfonates because of this guy right here, right? This guy, sulfonate, right? They're all incredibly good leaving groups, right? They're excellent leaving groups, right? But they're quite large, and so we usually just abbreviate them in their drawing as OMS, OTS, or OTF. You'll see OTS a lot, right? The tosylate group. The tosylate group is what is in the leaving group table from the last lecture. Okay. So sulfonates are such good leaving groups because they are very stable, like halides and conjugate bases of strong acids, right? And you can see why they're so stable. Look at all the resonance that's occurring here, right? They're all resonance. They're very resonance stabilized, okay? And then in addition to that, based on their pKa values, they're also very strong acids too, right? So which of the following sulfonate is the best leaving group? Probably the one that's the strongest acid, right? Which is negative 14 pKa. That's stronger than sulfuric acid. Sulfuric acid was what again? Negative 9 pKa, right? So these guys are super stabilized. Their lone pairs are super stabilized. Their conjugate-based lone pairs are super stabilized, and that's because of all the incredible resonance that's happening, which makes them very good leaving groups. Why are they good leaving groups? Because they're quite happy on their own, okay? So they leave you. They just leave you, okay? Sulfonates are made from corresponding alcohols, right? So you can have an alcohol here, okay? And the alcohol can do a little substitution reaction here where it does a nucleophilic attack on that sulfur there, and then the chlorine leaves, right? Okay, and so you get this oxonium ion, right? A pyridine can come over here, pull off that proton from the alcohol right there, and that bond comes down, neutralizing that oxygen from positive to neutral charge, right? Restoring its missing electrons, okay? And that gives you alkyl tosylate. So just notice though, right? We're just strapping the tosylate group to the oxygen of the alcohol. There is actually no change in the carbon atom of the OH group, right? So there's no change in this carbon atom at all, right? It's all happening with the alcohol group. Alcohols are not good leaving groups, right? But now we have a good leaving group once we add in some tosyl chloride and some pyridine, as you saw here. See? Good stuff. Good stuff. To envision then, so alkylsulfonates envisioning products, to envision the compound that we can synthesize from an alkyl tosylate, we treat them as you would treat any alkyl halide, right? Because just like alkyl halides are good leaving groups. Okay, so say we have a primary tosylate right here, and we treat it with some base, okay, with a strong nucleophile or a strong base. A primary substrate gives mostly SN2 with little E2, right? So here, the major product would be the SN2 product, where the tosylate leaves as a leaving group because the hydroxide comes over. I always draw it on there, but this is not unimolecular, so really it should be like this. Strong base, right, with its minus sign. Comes over there. Tosylate leaves, right? And you get this substitution reaction. Okay? Get the substitution reaction. On a secondary tosylate, right, with a strong nucleophile, strong base, a secondary substrate, right, mostly gives you the E with little SN2. Right? Yeah, so we'll have the proton from here come off. Kind of did that backwards, but that's okay. You get the idea. All right, that comes down, and the tosylate leaves, and that's why you get the major E2 product there. All right, the major E2 product. Alcohols can also be used in substitution and elimination reactions and used as a starter material to make alkyl halides and alkenes. Okay, so say you have a ethanol right here, right? Well, really, it's a tertiary alcohol, right? But if that were just a carbon there instead of an R, it would have been just an ethanol, right? The alcohol. Anyway, in this primary alcohol right here, right, we can treat it with some HBr, hydrogen bromide, right? And then we get the primary bromide, right? Alkyl bromide. Okay. Quite simply, what's happening here is the bromide comes over, right, and does a substitution reaction. Okay. And then the alcohol leaves as water. Okay. So we need strongly acidic conditions to be able to do these kinds of reactions because hydroxide is a really bad leaving group, right? But water is a good leaving group. And that's why we use things like hydrogen bromide or bromic acid, right? Because the alcohol can deprotonate the proton first, right, from the hydrogen bromide, leaving behind the bromide ion to do the nucleophilic attack, and then the entire thing leaves as water, as you see. Right? And the whole thing leaves as water. And so that's a basic SN2 reaction. My head's blocking the water, so let me show you that real quick. Yep. See? Basic and SN2 reaction. But in this case, we have a very strong acid helping here. Right? The bromide acts as the nucleophile. The proton from the acid will protonate the alcohol to make it a better leaving group, because water is a way better leaving group than alcohol is. So alcohols, SN2 or SN1, right? The mechanism will either be SN1 or SN2 depending on the substrate. Primary alcohols react via SN2, but secondary and tertiary alcohols react via SN1. So here's a tertiary alcohol right here, okay? Excuse me. Here's a tertiary alcohol right here, okay? And again, it's the unimolecular right here, because it's going to come over here and just pull off this proton from the hydrogen bromide, giving you the water attached to this alkyl, right? Which water is a good leaving group. Water can leave as a leaving group, leaving behind a tertiary carbocation. The bromine can come over, do a nucleophilic attack, and then you get the tertiary bromide. So strongly acidic conditions are protic conditions, right? Which would favor the SN1. But since primary carbocations are so unstable to form a primary alcohol, but since primary carbocations are too unstable to form, right, a primary alcohol will react via SN2 mechanism. Okay. And what that means then is just so you know what it's saying, right? This reacted in the SN1 reaction because a tertiary carbocation is stable enough to be formed, right, after the alcohol leaves, right? Both tertiary and secondary. But primary carbocation is not stable enough to be on its own, right, before the leaving group leaves or after the leaving group leaves. So if you had something like this, right, it would be super unstable. And so what you would have to do is, instead of going through SN1 like we did up here, you would go through SN2, where the nucleophile attacks first. Right? And then, I attacked the wrong carbon. Wait, what am I doing there? Oh, that's what happened is because it's supposed to be there. There it is. Ignore that. There we go. And then, so the nucleophile attacks the carbon down here, right? And then this leaves. What am I saying? This is. Oh. I have drawn a primary carbocation, and there's no. And I'm trying to do an SN2 reaction, and there's no leaving group there. There's already a primary carbocation there. It's my bad. Let me try that again. Right? So if you had a primary carbocation, right, that is too unstable to just be on its own, right, after leaving group leaves without having a nucleophile there to take its place. So, so the leaving group leaves being the alcohol, right? So really it has to be where the OH is still there as the alcohol, the leaving group, okay? And then the nucleophile comes over, right, does that attack there, and then the alcohol leaves, right? You can't form this primary carbocation is not stable enough. So when you have a primary alcohol, it's always going to do SN2, right, with the nucleophile and the substrate. Whereas if it's a secondary or tertiary, it's stable enough, right, because the tertiary and the secondary carbocations, they're stable enough where it can lose its leaving group, in this case alcohol, and still be stable enough to continue to react. Alcohols will undergo E1 elimination when reacted with sulfuric acid, right? So we have concentrated sulfuric acid here, and heat, right? And what will happen is that the alcohol, right? The alcohol will get protonated by the acid, okay? And then you'll have the water now attached to the alkyl group, and then water is a good leaving group, so it just leaves on its own, right? And when it leaves on its own, when it leaves on its own, a proton over here will be deprotonated by the water. I have to draw water again over here because I'm trying to do it all in one structure because I don't have any room. Like that, and then like that, and then we get the alkene plus water. Okay? Alkene plus water. So again, the strongly acidic conditions are protic conditions, and that favors E1 for secondary and secondary and tertiary substrates. Okay. And what I drew up here literally is down here. I should probably read the rest of the slide before I start drawing craziness. But it wasn't crazy. It's right. I just didn't realize it was already drawn at the bottom there. Right? So the H2SO4 there, of course, is making this H3O right here, right? The H3O plus. And then so the alcohol comes over, pulls the proton here, leaving you with a water, right? And then the water on the alkyl leaves, the alkane leaves, right? And then the other water comes over, pulls off the proton, and then you have fulfilled that carbocation with a double bond, right? And that's the E1 mechanism. So it gets us to this point here, where we have synthetic strategies and overviews, okay? The whole point to organic synthesis is to make valuable complex compounds from cheap, readily available starting materials. You know how to make a variety of compounds starting with an alkyl halide now, right? So here's an alkyl halide right here, okay? And just treating an alkyl halide with some base, sodium hydroxide, will get you to an alcohol, right? Or treating it with some sodium cyanide will get you to a nitrile, okay? If you take that alcohol that you just made with the alkyl halide and the base and treat that with some strong acid like HBr, you'll go back to your alkyl halide, right? You continue to treat that alcohol with some tosyl chloride and pyridine, and what do you get? You get our awesome leaving group, the tosylate, right? The alkyl tosylate. You can reverse that reaction by treating it with some more hydroxide, and you'll get back to the alcohol. Okay. You can treat tosylate with tert butoxide and get the alkene product, right? You get an alkene. Or you can treat the alkyl halide with tert butoxide and also get the alkene, right? Also get the alkene. You can treat it with the sodium methoxide, the alkyl halide with sodium methoxide, and you can get an ether. Okay. You can treat it with the sodium thiol here and get a thiol, an alkyl thiol. You can treat this here with sodium, I think that's actually acetic acid. Sodium acetate, that's what that is. Yes, that is. You can treat the alkyl halide with sodium acetate, and then you'll get an ester, right? So, quite simply, just knowing that you have an alkyl halide from the beginning, you can treat it with all these different kinds of reagents, and you'll get all these other products, right? It's pretty cool. Whew. Synthetic strategies, many possible reactions, right? In order to envision how a desired compound can be made, you need to be able to recall these reactions and that you can use. Meaning, you have to memorize these reactions, okay? You have to memorize these reactions. Okay? So here we have another alkyl halide. We treat it with tert butoxide, and what do we get? We get an alkene, which is the Hoffman product. We treat it with the sodium hydroxide. We get another alkene as a ZZEV product, right? Or you can treat it with alcohol and get an alcohol. Treat it with water. Treat the alkyl halide with water, and you'll get an alcohol, right? Treat that alcohol with concentrated sulfuric acid, and you get the alkenes again, right? We can take our alcohol here, treat it with some tosyl chloride and pyrimidine. I think it's pyrimidine, right? And you'll get the tosylate, which is the awesome leaving group, right? And then treat it with acid again, or tert butoxide, hydroxide or tert butoxide, and you'll be able to get the alkene products again, right? So literally so what this is demonstrating to you is that you can treat any alkyl halide with various reagents, and they'll give the corresponding reagent product according to whether it's an SN2, SN1, E2 or E1 reaction, right? And you can predict its products. So there's this thing called retrosynthesis, where you look at a product and you figure out what you got to do to make that product. This is called retrosynthetic analysis. Okay. If you're thinking of building a brick house, you must first imagine what that house looks like first, and then decide what bricks you would use to make it. Right? Same thing in organic synthesis. First, look at the desired product and and from there we decide what substrates and reactants we need to use to make it. Okay? I told you we would get to this point today, right, where you're starting to make things just by looking at the product, right, and you're going to choose reactants to make the product. So here's an example. Okay? Here's an example. Ooh, we're about to do a synthesis here. Got to stretch. Got to pre-game for the synthesis. Okay? Suppose that you want to synthesize this ether right here. Okay? Synthesize that ether. The first thing you need to do is identify a bond in the target molecule that can be made using one of the reactions that you already know. Okay? Well, turns out that this bond here is something you can make. Right? We can make this bond by SN2 reaction between an alkyl halide and alkoxide. Right? So here's the alkyl halide right here. Right? Bromo 1, 2, 3, 4, 5 pentane. And then sodium methoxide. Okay? Sodium methoxide. And you know you could do this, right? Because it's a substitution reaction. Okay? The retrosynthetic arrow is used to show that we're thinking backwards in regards to the reaction that we can do, right? And if you think about this as being the starting material, because it is a starting material, right? You'll have the ethoxide ion right here from sodium methoxide, right? And it will do a nucleophilic substitution right there, right? Nucleophilic attack right there. Bromine will leave as a leaving group. And then you have ethoxide now attached there by the oxygen, via the oxygen, right? And it was a simple SN2 reaction. It's another way to make it. So there are two carbon-oxygen bonds in an ether. So we could also envision an alternative SN2 reaction to make it, right? This time, the bond that we're going to make is forms from on that side, right? And that's also going to be we can do that with SN2, and we do that by using an alkoxide ion right here, right? And this time we'll have an alkyl halide, right? Thinking backwards again, right? Thinking backwards. The same thing happens again here. We end up with an alkoxide ion comes over here. That leaves as a leaving group, bromine does, and you have now this ethyl attached to the oxygen, giving you the ether, right? You'll find that thinking backwards this way more than when thinking backwards this way, more than one reaction will come to mind when you're trying to make a target compound. Okay? Step 3. What was that? Step 2? What was step 2? Oh, step 2 was draw the substrate and nucleophile necessary for the reaction, which we did that, right? Okay, step 3. Verify that the reaction you propose will be reasonable. Okay, so here goes one of them right here. It's a primary halide, which is a good substrate for SN2s. That's correct. And then also we have a strong, unhindered nucleophile, right? Which is also good for SN2 reactions. So yes, we would expect this reaction to work. And then you draw the reaction in the forward direction, right? And you see if it makes it correct, right? And while we're at it, why don't we just use an aprotic solvent, like DMSO, to put it in, since it's an SN2 reaction? I'll tell you why in just a second. Put a pin in that. Okay? Put a pin in that. So, I mean, how many times I'm going to draw this, but, you know, we have the alkoxide come over here and attack that carbon there, and that leaves there, and then gives you this SN2 reaction, right? in SN2 reaction, why not use an aprotic solvent? Right? Why should we use an aprotic solvent? Put a pin in that. It's in the upcoming slides. So, take a look at this guy. What reactants would you need in order to make the following compound as a product of a substitution reaction? Okay? Now, I want you to try this on your own. And if you want to check your answer or you just don't know what to do, just go to Skill Builder 7.8, Retrosynthesis and Synthesis in Wiley Plus and in the textbook, and it'll walk you through it. But I want you to practice this on your own. Okay? Make that guy for me. All right. Solvent effects. Right? I told you to put a pin on that DMSO thing, right? This is why. Okay? So, SN2 reactions require a polar aprotic solvent. Okay? Protic solvents engage in hydrogen bonding and stabilize the anionic species such as good nucleophiles. And in an SN2 reaction, what do you need? You need a good nucleophile, right? On the other hand, though, aprotic solvents stabilize both anions and cations, right? So how do these factors play into the strength of a nucleophile in a protic versus aprotic solvent? And we'll see that in just a second, right? But I just want you to take note of what is a protic solvent and what is an aprotic solvent. Quite literally, aprotic solvents are things that have protons on it, right? And these protons are attached to electronegative atoms, right? And so they can do hydrogen bonding, right? Whereas protic solvents that are polar solvents that are aprotic, right, don't have protons that can just easily do hydrogen bonding. Okay? For example, acetone right here, DMF, right? Here's dimethyl sulfoxide, DMSO right there, right? And here's hexamethyl phosphoramide, right? No protons that really can do any kind of hydrogen bonding, right? So that's the big difference. Protic solvents, hydrogen bonding. Polar aprotic solvents, no hydrogen bonding, because those protons they have are not connected to any electronegative groups. So what are the implications then? Oops. What are the implications then? Well, let's look at some experimental data first, right? It turns out that experimental data indicates that an SN1 and E1 reactions are much faster in a polar protic solvent, right? Which is actually in conjunction to, right, which is actually contrary to SN2 reactions, right? In an SN2 reaction, a polar protic solvent, right, in a polar protic solvent, right, the rate is 43, but in a polar aprotic solvent, the rate is 6,500, right, for iodine. So as we go down this chart, you can see that due to a polar aprotic solvent system, right, we can see how much stronger these nucleophiles get, or their rates get, right, due to a polar aprotic solvent, right? In contrast to in an SN1 and E1 reaction where they prefer protic solvents. Okay, so let's look at that on a graph. For SN2 reactions, a polar aprotic solvent is best, right? Overall. For an SN1 reaction, a polar protic solvent is best. Okay? So you can see here in this potential energy diagram, right here, right? For a polar aprotic solvent, okay, for an SN2 reaction, it actually increases the potential energy of the nucleophile all the way up there, making it so that the energy of activation, right, for a nucleophile and the reactant much smaller than it would be if it were in a protic solvent. That energy activation is much higher. Energy of activation is much higher, right? So aprotic solvents raise the energy of a nucleophile. Uh-oh. Emergency alert. DPS issues a blue alert on behalf of a Wise County Sheriff Office for a Rolls Royce Howard Wood 43 62 200 pounds. Not seeing this. That's weird. Okay. Let's start this over again. Okay. Overall, for For SN2 reactions, a polar aprotic solvent is best, as we saw in the chart previous slide. The chart in the previous slide. And for SN1 reactions, a polar protic solvent is best. Why is that? Well, notice here in this graph, where we have the reaction coordinate graph again, right? And potential energy is on the y-axis. For a polar aprotic solvent, right, if a nucleophile is present in a polar aprotic solvent, it actually raises the potential energy of the nucleophile all the way up here, right? And then the energy of activation between with the reactant, right, is very small, right? Contrast that to having the nucleophile in a protic solvent, and now the energy of activation is this much, which is a lot higher, right? A much larger threshold to overcome. So, aprotic solvents raise the energy of a nucleophile, which results in a lower activation energy and a faster SN2 reaction. Okay. Whereas on the other hand, for an SN1 reaction right here, right, protic solvents stabilize a carbocation intermediate, which results in a lower activation of energy and a faster SN1 reaction, right? Which makes sense because you have when you have an SN1 reaction, you're going to get some kind of carbocation, right? When your leaving group leaves on its own, right? It leaves on its own, so now you're going to get a carbocation, right? And when you have a polar solvent, a protic solvent, right? It can do hydrogen bonding, right? And it can stabilize. It can then stabilize that carbocation, right? That carbocation intermediate. And when it stabilizes that carbocation intermediate, it brings the activation energy much lower, right? And this is where that carbocation intermediate is, right there, much lower. And so the reaction is faster in an SN1 reaction when you have a protic solvent, because it stabilizes the carbocation. Okay? And just so you can see it graphically, not just, you just saw it graphically, just so you can see it visually, why is it that DMSO, right, an aprotic solvent, right, why can't it not stabilize, why can't it stabilize carbocations or other charged species, right? Well, the reason why is because the partially positive sulfur here, right, that would be used to otherwise stabilize a negatively charged nucleophile or base or whatever, right, is actually hidden back here behind all the steric hindrance of this methyl group, these oxygens here, right, and these electrons. So it's impossible for it to actually do any kind of stabilization of ions, right? Because its partially positive side is completely masked by all the things around it, right? Nucleophiles are less stable and thus are more reactive in an aprotic solvent because of that, right? Since DMSO can't stabilize it, it makes that nucleophile much more high energy, and if it's more high energy, then it has less of a threshold to reach to reach the activation energy barrier, right? To make an SN2 reaction occur. The activation energy will be lower, and the energy will be faster, and the reaction will be faster. And the moral of the story is, aprotic solvents are best for SN2 reactions, which I already went through this chart, this particular graph in the previous slide. That actually ends our lecture today on alkyl halides, nucleophilic substitution, and elimination reactions. And so I know it was a long one, and there's a lot of information there, but it's going to be okay. You have an assignment that's going to be posted. That's going to be on the nucleophilic substitution and elimination reactions. That will be due tomorrow by 7:59 a.m. Quiz 6 is also going to be assigned, and that will also be due at the same time, all right? And just a reminder, you have exam 3 tomorrow, okay? On June 18th, 2021, okay? I will be available on Thursday in office hours, although someone has already booked me for my office hours. Excuse me. So if you need to talk to me, send me a Teams message or a Teams IM or a an email with your question, or you can try to schedule a different time to meet with me over Teams on video chat. Okay? Good luck on your test tomorrow, and I will see you in the exam solutions review. Solutions video. Well, actually, I guess you would see the quiz solutions video first, right? So, the quiz. Yes, the quiz 6 solutions video first. All right. All right. Good luck on the exam tomorrow.